Let's take a look here at the machine. The crank and the test piece are seen here.
Alright, so Luther is going to apply tension to this steel test piece. There he goes, he's going to start cranking and we see some deformation, and then we're going to see it actually break right here.
Watch again here in slow motion, and you can actually see the necking occurring in the piece right before it snaps.
Well, you can do the Excel.
Alright, so the next test specimen we've got here is aluminum. And this aluminum piece actually elongates a good bit before it begins to neck and then break. Alright, here we have the slow motion for the aluminum test sample. It's hard to tell, but it actually elongates a good bit before any necking begins. And once necking begins, there's not a whole lot right before it fractures. Good. Moving on to our next specimen, we have brass. We're going to do this in the same way. Luther's going to tension it up, and we're going to watch as it elongates in the elastic region, and then it will neck very quickly and then snap. Here we have the slow motion for our brass test piece. As we apply tension to this test piece, there's a little bit of elongation in the elastic region, and then as we start getting into the plastic region, we'll notice deformation and necking occurring right before it fractures. We can see here the necking is starting to begin. You can see it just a little bit and it gets more drastic, but it'll break rather quickly without a whole lot of necking. Alright, here we go. This is our first graph right here. This is our steel. We can see here that this straight line highlighted in yellow right here represents the elastic region of our specimen. And then we can see here how it starts to deform and necking occurs all the way down here until the specimen actually breaks. Now if we come over here, we see our aluminum test piece. For our aluminum test piece, we can see that we have the same type of graph with our highlighter region, which is our elastic region, and then our plastic region up until the point where it actually snaps. And then finally, over here we have our brass. Our brass, same thing, same exact graph, type of graph, and we've got our elastic region moving into our plastic region, and it deforms, and then it's not on the chart here, but it we can get that here in just a second. That doesn't do it. There you go. Now it breaks right here. All right, now looking at our modulus of elasticity for each of our materials should be represented by the slope of a best fit line for our data within this highlighted region. So we have here that our slope m is 4.51 times 10 to the 10th, and this is in pascals. And we have plus or minus 2.4 times 10 to the 8th pascals. Then here we have 2.59 times 10 to the 10th pascals, and then down here we have 3.14 times 10 to the 10th pascals.
Now, as you can see here, we have a cold front moving up to the north, which is going to be...
Bryce? Wrong.
Oh, wrong job. Okay, I'm supposed to tell you what exactly these charts mean. Basically what we have here is on the upper left, we have our graph for the tensile strength of steel. And over on the right, we have tensile strength for aluminum, and down here on the bottom, we have the one for brass. Now, essentially what we did was we took samples and we pulled them apart until they broke. Here, you basically see that by taking the stress applied to the sample over the strain of the sample, which is effectively the movement of the sample before the breaking, you can gain the Young's modulus. The Young's modulus for steel is 4.51 times 10 to the 10th pascals. For aluminum, we got 2.59 times 10 to the 10th pascals, and for brass, we got 3.14 times 10 to the 10th pascals. However, our problem is that the actual publicized information for Young's modulus on the Pascal system, capstone system is on their website is that it's significantly lower. Our measurements are significantly lower than what they have publicized. Our steel is about 45 gigapascals, whereas theirs is 200. Our aluminum, 25, theirs is 70. And our brass, 31, where theirs is 80. We did encounter some problems, though, with calibration for our software. Our software did not recognize the type of calibration operations we wanted to accomplish. And anytime we went to the calibration menus, the options for calibrating this particular tensile strength machine were never represented or presented to us. We do know, however, that our calculations are consistent. If we can go to the second page, we did a second test on steel. Steel registered at 4.84 times 10 to the 10th pascals, which is about 48 gigapascals. This is very close to our original test, which was 45 gigapascals. Basically, what we were able to accomplish is that there definitely is some calibration issues. There's definitely something going on to cause such a very wide difference in the measurement for the Young's modulus. Over here, we broke down the actual percent errors and what they're actually supposed to be. So our percent error for aluminum is 57%. As we go higher in what the Young's modulus is supposed to be, the percent in difference actually increases. This leads us to believe that there is a type of exponential error happening with the calibration of the machine. Over here is a graph we made up showing the percent errors and the expected Young's modulus. And the relationship, as you can see, with this best fit line actually comes here and makes its curve upwards, which if we had more data points, we believe it would actually show an even greater curve, which would be more indicative of an exponential curve. However, with our 3 points, we can surmise that whatever is throwing off our measurements is doing so in an exponential way.
Bryce, are you done with this dictionary and thesaurus yet?
Keep it open.